Hi, grade 8s. In this unit, we've been talking about the properties or characteristics of fluids. In the last video, we talked about the relationship between mass and volume, which leads right into today's topic, density. Let's start by reviewing what we've talked about so far concerning the properties of fluids. First off, we know that fluids are made up of particles of matter. In other words, they have mass. This particular property actually applies to all states of matter, so it's true for solids as well as liquids and gases. Secondly, we know that fluids take up space or have volume. Again, this property applies to all states of matter, solids, liquids, and gases. Recently, we spent a fair bit of time exploring the next property. Fluids can flow and can be thin or thick. This was where we considered viscosity, which is a fluid's resistance to flow. Now, solids can't flow, so this property only applies to fluids, that is, liquids and gases. Today, we're going to start talking about a new property of matter. And I know you're going to be all very excited by this. So our new property is that every substance or type of matter has a particular density. You can talk about the density of solids as well as liquids and gases, so this is a property that applies to substances in any state of matter. In the last video, I asked you to make a prediction about whether the mass and volume of a particular substance are related. Specifically, as the volume of a particular substance goes up, meaning that the substance is taking up more space and you have more of the substance, what happens to the mass? Does it go up too? Does it go down? Or does it stay the same? Conversely, as the volume of a particular substance goes down, meaning that the substance is taking up less space so that I have less of the substance, what happens to the mass? Does it go down too? Does it go up? Or does it stay the same? To investigate this question about fluids in our school lab, we took samples of common household fluids, distilled water, salt water, syrup, and vegetable oil. Then we measured out different volumes of each fluid, starting at 50 milliliters and ending at 300 milliliters, going up in increments of 50 milliliters. In the body of the table, you can see the different fluids listed with the mass in grams for each volume of a particular fluid. So here would be the masses for distilled water, here would be the masses for salt water, for syrup, and for vegetable oil. For each volume of a substance, we measured its mass in grams using a triple beam balance. Now, this is actual data collected by previous grade 8s at our school. We had several groups of students doing the same experiment, so to include all of the data and to give us the best reliability, for each cell in the table, we calculated an average mass. So all the values in the body of the table are averages. Now, if you're anything like me, you might have a difficult time visualizing what this data are telling you when it's displayed in a table like this. So let's look at a graph. So here's the graph. Now, I've put volume in milliliters on the x-axis. Just give me a minute here. I'll get my highlighter. So here on the x-axis is where I show my volume. On the other hand, I put my mass in grams on the y-axis. So there's my mass. Now, I'm just going to get rid of those two lines so they don't confuse us later on. There we go. Now, then I've plotted a separate line for each fluid. So I've got my line here for syrup. I've got my line here for salt water. I've got my line here for distilled water, and I've got my line here for vegetable oil. What this graph shows you is the relationship between mass and volume for each of these substances. In other words, it shows you what happens to the mass of a substance as you increase the volume. Now, before I go on talking, because really, I do talk too much, I'd like you to take a moment and look at the graph on your own. What do you notice? How is mass related to volume? Well, I hope you noticed a couple of things. First, the data points for each liquid fall in a straight line, and the line goes up and to the right. This is what we call a positive relationship, meaning that the variables, in this case mass and volume, go up and down together. When one gets bigger, so does the other one. When one gets smaller, so does the other one. So here, what it's showing us is that as the volume goes up, the mass, or the amount of stuff, the number of particles you have, also goes up. And it makes sense. As long as you're keeping the substance the same, the greater the volume you have means that you have more of that substance. If you have more of the substance, you have more particles of matter, so you also have more mass. Now, here's the second big thing to notice about the graph. The lines for the different liquids didn't all go up at the same rate. In other words, the lines for the different fluids have different slopes. For example, the line for syrup goes up much more steeply than the line for vegetable oil. That means for every increase in the volume of the syrup by 50 milliliters, you add more matter, you add more particles than you do when you add 50 milliliters of vegetable oil. In this case, every time we added 50 milliliters of syrup, the mass went up an average of 69 58 grams. But every time we added 50 milliliters of vegetable oil, we only added an average of 48 28 grams of mass. So if we were describing these fluids, we would say that the syrup was denser or had a higher density than the vegetable oil. So let's boil this down to the basics, the key things that you have to remember. First off, density is considered a property of all matter and is defined as the mass of a substance per unit of volume. So basically, density is just a ratio of mass to volume. Any substance that you can think of, whether it's a solid, liquid, or gas, has a density. So, for example, if you had a big old chunk of gold, first off, lucky you, but secondly, a chunk of gold would have a density. If you had a glass of tap water, the water in the glass would have a density. And if you had a helium balloon like we used to get at birthday parties, the helium filling the balloon would have a density. Now, you wouldn't want to have to organize a big data table or draw a whole graph every time you wanted to look at the relationship between mass and volume for a particular substance. Scientists have helped us out though. Yay, scientists! By giving us a nice, easy calculation we can use. And we can use this calculation for substances in any state of matter, solids, liquids, or gases. So here's the formula for calculating density. Density equals mass over volume. In other words, you're dividing the amount of matter you have by how much space it takes up. Now, you don't always need to write the full words. You can also just write the formula using variables as D equals M over V. Now, let's take a minute and look at the units of measurement that we'll be using. The fact that the calculation of density is based on both mass and volume is reflected in the units of measurement that we use for density. For solids, we typically show density in grams per cubic centimeter. For liquids, the usual unit of measurement is grams per milliliter, and for gases, we usually show density in kilograms per liter. In each case, the first part of the unit of measurement refers to the mass of the object or substance. This is in the numerator of the ratio, so it is listed first in the unit of measurement. The second part of the unit of measurement refers to the volume of the object or substance. This is in the denominator of the ratio, so it is listed second. Let's take one more look at the formula for density. Every time you calculate the density of a substance or object, you're calculating how much mass, how much matter you have in each unit of volume. So if it's a solid like gold, you're saying, how many particles of matter do I have in 1 cubic centimeter? If you're looking at a liquid like tap water, you're saying, how many particles do I have in 1 milliliter? For gases like helium, you're saying, how many particles do I have in 1 liter? What this means is, the higher the number you get for density, the more closely packed together the particles of a substance are. If the density is lower, it means that there is more space between the particles. To get a sense of what this might look like, imagine that we had a super powerful and unbelievably powerful microscope, and we used this microscope to look at the particles of matter in different substances. So I'm going to pull up a circle that could represent our field of view for this microscope. And these purple circles are going to represent the particles of, we'll call it substance A. We could also use our pretend microscope to look at a second substance that we'll call substance B. Again, the small circles inside the field are going to represent the particles of this substance. I've made them a different color because since this is a different substance, it will have different particles. For substance B, you'll notice that the particles are much more closely packed together with much less space in between them than you see in substance A. As a result, if I were to calculate the density for both substance A and substance B would have a higher density. To give you some examples of densities of actual substances, let's go back to my examples from a few slides ago. A sample of pure gold would have a density of 19 and 3200 grams per cubic centimeter. That means for every cubic centimeter of gold, you have 19 and 3200 grams of matter packed in. A sample of pure helium, on the other hand, would have a density of 179 thousandths kilograms per cubic meter. You'll notice that the unit of measurement changed because now I'm dealing with a gas instead of a solid. These two substances, I have to admit, I cheated and looked up their density in our grade 8 science textbook, so I'm going to show my resource there. For tap water, I actually calculated the density myself. I went to the kitchen, got 100 milliliters of water, and found the mass. So the tap water at my house in Aurora, Ontario has a density of 9/10 grams per milliliter. Again, notice that now I'm dealing with a liquid. My unit of measurement has changed to grams per milliliter. For a mixture like tap water, the density may differ from place to place depending on the exact combination of substances in the mixture. For example, tap water in Aurora may have more minerals than tap water in some other locations. Some houses may get water from city pipes and have water with fluoride, while if you have a house drawing water from a well, it won't. And all these differences will mean that there are different mixtures of particles which will affect the density. On the other hand, all samples of a pure substance like gold or helium should be made up of the same type of particle. Pure gold would be made up of gold particles, pure helium would be made up of helium particles, and all the particles of a particular pure substance would be identical to each other and would be at a particular distance from each other. What that means is that the density of a particular pure substance should be the same no matter where in the world you find it. So, for example, pure gold found in Canada should have the same density as gold found in the United States, which should have the same density as pure gold found in Russia, or Peru, or in South Africa. As a result, if we have a mystery substance and we know its density, that can give us a clue about what the substance might be. That's it for now. Just a quick look at the references and resources that I used in making this slideshow, and we'll continue on next time.